Welcome to Coursera's Instrumental Analysis. This is going to be a focused lecture where we go through 4 examples of calculating concentrations of unknowns using internal standards and the method of standard. My advice is to try to do these problems yourself beforehand. You can find them posted online under resources, or you can simply stop the lecture before I do the problem, try to do it on your own, and see how your answer compares to mine. One note about the examples I'll be working is in this particular video lecture, I am not going to be using Excel. I think it's important that you know how to address these problems in the absence of Excel. I'll be doing in lecture 8 a lot more Excel work. Okay, so in this first example, it's a classic internal standards example. And one of the things you can do is figure out what the unknown that you're looking, what the internal standard is and what the unknown is from the question. So the fact that you're being asked to find the lead means that lead is the unknown. And that would mean that copper is the internal standard. So that's kind of the first thing you have to do. So the key expression you're going to write down and think about when you're handling internal standards is this one, that the signal of an atom ratio to the signal of the internal standard, in this case copper, is going to be equal to what I called the F factor, or a constant, times the concentration of lead over the concentration of copper. This is a lot like a single point calibration, except we're using ratios because we have the internal standard. Okay, so let's plug our numbers in. It's almost always true that there's some data in a question like this that are kind of your standards. And in this case, that's going to be the first data set given, that 435 microamps divided by 245 microamps. And we know that this is our lead and this is our copper. And if you go up here, you can kind of find them. So for example, here is the copper channel, and here is going to be the lead channel. Finishing out that expression. So hopefully you can see how the lead data set and the copper data set fit into our calculation of the standards. After all of that, we can calculate the F factor here to be equal to 0.670, and it is. Now we're going to move on to information about our unknown. So in this case, our signals are given in the problem, so we know something about those signals. I'll use the same colors. Now in this case, our F factor is going to be the same, and we do not know the concentration of our lead, but we do know, because it was the internal standard, the concentration of our copper. And so you can solve for X to be 0.0372 molar, or if you want to take sig figs into account, probably better to do 0.037 molar, because 2 sig figs is what we use for this problem. Now interestingly, if you didn't use internal standards and you only used your lead data set, and that's not too surprising. If you only use your lead data, you're not taking advantage of the fact that the internal standard is going to correct out for perhaps in the second experiment you were running a little bit high. And so that's one example of why when you get data with internal standards, you really want to make sure that you treat the ratio of the unknown to the internal standard, both in the signal and in the concentrations, as your primary variable. Okay, but we can see here that our correct answer is right there. This is a really similar problem, so I would encourage you again to stop the video and try to do it yourself. The basic formula, just like last time, is going to be the signal of gadolinium, because that's going to be our unknown, so it's just convention to put that on the top, divided by the signal for europium. That's going to be equal to some other F factor unique to this experiment, concentration of gadolinium over the concentration of europium. So now we're going to work with our standard, and the goal of this calculation is to find the F factor. And that's just going to be 32.3 millivolts of gadolinium. And we're going to have an F factor, which we're solving for. And if you go up here, you can see that we were working with 5.3 ppb gadolinium when we got that signal. Now let's divide by the europium information. Well, europium is just going to be given by this in our standard, and we were also given that concentration. So here's our europium, And there's our concentration over here of europium. And if you work that math out, I calculated an F factor. Now we have to work with our unknowns. So in this case, it's going to be 64.2 millivolts of gadolinium, because as you can see, and the europium in that final sample had a different signal. The F factor is the same here. Now, I don't know the concentration of gadolinium. Remember, that's what we're being asked. But I do know the concentration of europium in these experiments, because in this unknown, we were given that. Okay, so you can calculate that X to be 11.7 ppb gadolinium. And one of the important things to realize, so you can see that it's always important to use your internal standards if you have them. And honestly, in this case, I would say you do have one example of a sig fig that's equal to only 2, so probably I might report 12 parts per billion. All right, I want to move on to a standard addition example. Now, standard additions are handled a little bit differently. Just to remind you of what goes on in standard additions, you have a situation, and in this problem, let's sketch it out because that may help you reason through what you do. So in a standard addition problem, your 0 is not really no lead, because what you're doing is adding lead to your sample. So your x-axis here is not the total amount of lead, but only the amount of added lead. So the 0 data set is going to be important, and in this case, that's 0. And what that tells us is that this offset is going to be related to the amount of lead that's in that first sample. And then we're spiking this sample with a certain amount of material. So we can tell that we added some amount of material of lead, and when we added that much, and that's described, by the way, right here, that's the extra lead that we added. And when we did that, we got an increase in our signal. We went from 102.3 to 187 milliamps. So we got a data point way up here, and we saw an increase in our signal, and we had an increase in lead. So what we can calculate then is the slope here in a single point calibration, and from that we're going to be able to go back to our y-intercept and then figure out what concentration that must have been. So first off, though, we have to deal with the niggling little problem of the fact that we did this funky dilution. So we first have to calculate how much lead did we actually add to the sample. So what I just did is took that green data set, and 5 mils of the lead that was 1.04 molar was put into probably an volumetric flask and diluted up to 150. And so that gives us a new concentration of lead of 0.0347. So over here, we know this is 0.0347. As we find the slope. Now remember, the slope can be the instrument response function, or can be the response function. I'm going to call it slope in this problem. So our slope is just going to be equal to rise over run, change in y over change in x. Well, the change in y in this case is 187.3 milliamps, because what happened when you added that material is you increased your signal to 183. And you can see that information right here. So that's how much it went up. But we have to realize that it didn't just go from 0 to that point. It already had some there, so we want to subtract that out. There's the offset due to whatever lead's present in our wastewater. Now on the bottom, the amount that we added was just 0.0347 molar. And when you do this, you're going to find 2450 milliamps of signal per molar lead. Finally then, we're going to simply divide our y-intercept by the slope we just calculated. So we're going to take 102.3 milliamps divided by 2450 milliamps per molar lead. And when we do that, we're going to calculate 0.0418. Again, sig fig issues. Looking at this problem, you probably would report to 3, as I did. Okay, so let's do a second example of standard addition. So in this problem, what's a little bit tricky is you end up with 2 different ions you're thinking about, both calcium and zinc. But it's the same idea as before. If you drew your diagram, what's happening is you're getting information about one run here, which is effectively no added ions. And that's effectively your seawater sample. And then what you're doing is you're doing a second run after you've added some amount of calcium or some amount of zinc. And so this is added stuff, and this is a bigger signal. And what you're trying to do is calculate the slope with only 2 points, so it'll be pretty estimated. But what that's going to allow you to do is figure out for your y-intercept here what was the appropriate x value, because this slope is going to be the same everywhere. I'm referring to as this data point. It's the one after you added it. And since we have a dilution to deal with, we need to handle this information and figure out what the actual concentrations were at the end. So that's a pretty straightforward thing to do. You had 5 mils of calcium, and what you did is you know that that was 1 molar calcium, and so that was taken together. Those two things, sorry, this is liters, are going to be equal to moles of calcium, and you're simply dividing by 250 liters. What that's going to get you is 0.020 molar calcium. And you can go through a similar analysis because it's identical and come up with 0.020 molar zinc. So what we know is that's how much stuff we added. We added 0.020 molar. So now what we have to do is just calculate the slope, because the slope is going to be the rise over the run. And so in this case, for the calcium, and here I'll call it instrument, we'll call it instrument response function. That's simply going to be the amount of calcium that you started with in signal. It's going to be this signal minus that signal, just how much signal was there. And that's simply going to be 87.5 minus 34.5 milliamps divided by 0.020 molar calcium. And when you put all that together, you're going to calculate the instrument response function here of 2650, which is the same as the slope of the line. Let's do the same for zinc. Okay, so there we have our instrument response function. So if this was step 1, this is step 2, and now we're going to basically convert. So to do that then, I'll write it simply. The concentration of calcium is going to be equal to the 34.5 milliamp signal at calcium, and that's the signal we had up here. That's the initial value, so that's our Y signal here, divided by, of course, our instrument response function, 2650, and that's going to be in terms of milliamps calcium, divided by, in this case, molar calcium. And we work all that out, we're going to get 0.0130 molar calcium. And for zinc, I'm going to drop the unit so I can fit it in here. It's 124.2 divided by 2150, and that's just going to give us 0.0578 molar zinc. And the sig figs you probably carry here, scanning the problem, look to be about 3 sig figs. So this is correct, and this is correct. So I hope that's given you some examples to work with. Thanks so much. See you next time.